Okay, so let's start part 2 here for chapter 8, talking about multiprocessors. As we were just talking about symmetric multiprocessing, or well, multiple processors, in doing that, yeah, you get the benefit of you can kind of think of, pouring water into 10 different glasses, and it's really easy to think, oh, well, that one's kind of empty, so I'm going to fill it up. But a lot of the problems come in when you have to think about, okay, they're not water. There are things that are running, different things, and they might be running something that, is a very large job, might do a lot of I/O, and you take all that into consideration, and we can't think about it as a resource like liquid. We have to think about it as jobs, and that's why we kind of use the word short-term job scheduler and long-term scheduler and all these different, terms for it. But, the reality is that when we want to kind of use all these things at the same time, if it's two or more things that have access to one thing, then we have to worry about how do you synchronize things. And so there's a lot of words we use in computer science we don't like. We don't like synchronization. We don't like polling. We don't like waiting and blocking. All of those are just kind of headaches because we have to figure out how to manage it. So when you synchronize CPUs in how they, as an example here, deal with memory, think about some of the things we've talked about before. Is the memory available? Do I have access to it? How do we manage all that? So when we talked about MMUs and all the different kind of things we were kind of working on before, we have to take it up a notch, or I guess actually down a notch, because when we talk about a single process going and saying, I need memory, think about the idea that, let's say I have process 101. And process 101 says I need K of memory. So it goes and gets a K of memory, and let's say that that's what this memory is right there. So the process owns it. Now, it could be that process 101 does all that through CPU 1, and all that goes in, and all that's great. But then, just because of the logic, now the CPU scheduler said, nah, process 101, you're going to use 2. Now, I'm not bringing anything new to the party. I'm not doing anything. I'm just using a different machine now versus CPU 1 to go do something with my memory. And if I'm doing these writes and all this stuff at the same time, I'm still running into the same kind of problems. So, could it be that based on the schedule algorithm and everything, that same process could go through two CPUs at the same time? Maybe. That's again, an easy way to look at it, like we think about locks. If you lock something twice, you have a deadlock. It's more, how do we manage this, and how do we know that, we're not going to run into that problem? Now, this comes into more problems when you think about shared memory and other forms of how things deal with that. But it's just in the fact that if we have more than one thing, two or more things, acting on one thing or trying to manage one thing, you're always going to run into this problem. So one thing we could do is this whole kind of idea on, spin locks, and we've talked about this before. So maybe a little bit in the dining philosopher kind of ideas. And this one's really there, to avoid this whole cache thrashing, the reading, putting everything into cache, taking out, and then moving it around. And so, and what you have to keep in mind is this block here, this big block is shared memory. So this is a logical thing, the ability to do the lock, and then kind of as we've seen before, everybody just kind of spins on this and they get it in their turn, which makes it much easier. So once again, we see something that we've solved in for a different problem that looks pretty similar in the exact same way. So we can also look at it based on time sharing and idle. So this is an example where up here these CPUs are busy. So 0, 1, 2, 3, 4, they're busy. But then there's new things that need to get done. And so we have this priority scale, and we'll learn more when we get into Linux, which is based on Unix from back in the day, on prioritization and nice values and how we would kind of plug that stuff in. So this example, just take it for what it is. Don't think too much through it, but it means that because this is the highest priority, A is going to go first, then B, then C. So this is the queue. Then D, then E, then F. You follow the alphabet here. Should have mixed it up a little bit. But the idea is that since all of these are busy, nothing's happening. As soon as one goes idle, which is here, you plug A in there. And then let's say that this 12 CPU goes idle, then you plug B. Now, we could take this again and again, and we could do C, D, E, F, whatever. The thing that is never really talked about is kind of, what is the timing between these? And is other things getting kicked into the priority and what's being managed there? So, I mean, there's all this stuff going on, quote unquote, at the same time. So we have to be a little careful of not making it a little too simple and myopic. It's kind of this way that I can take a 16, CPU system and kind of grab things. But again, I'm grabbing this either blindly, not knowing if this is, a process that's been in queue forever. Does it have, it obviously doesn't have affinity because it just goes to the first one. We go to all our FAIR algorithms that we've talked about before, first in, first out, round robin, anything in the form of queuing and priority and starvation and all the other things. So it's interesting to kind of think about, this is a simple academic way to kind of do this. And this is really only coming from the fact that it's just popping things out of a queue, and there was no real point in putting a priority around this either. I mean, you could just kind of put this in A, B, C, D, E, F. I mean, it all flows that way anyway. So don't get too lost in that, but it just plugs in, right? We can also chunk these things up, and we can say, okay, well, let's split these things up into different kind of groups. And is this what a virtual machine would look like on your Type 2 hypervisor, where if I had 32 cores on my Mac here and I gave 4 cores to CentOS, that would be here? Yeah. That's kind of what we're doing here. So there's many different ways we can do this. And again, if you went and saw that source code for the CPU scheduler, you can kind of do whatever you wanted. So, do I want to, group things together and maybe take all my microservices that I build into a clone namespace that runs on itself, which is the whole Docker container, and give it its own group. So all microservices run in these 8. My OS runs in these 6. I do all of my guest compute OS stuff here, maybe one there. Something to think about. How do we break it up? Gang scheduling is another interesting one, where what you're really trying to say is I want everything to run when. So put everything into a group called a gang. So I'm kind of group scheduling or gang scheduling. So what you're trying to really achieve there is you want this thing to run. You want like A to run all the time, and it just might flip between CPUs. So you would have some queuing algorithm to say, A and B both need work to get done. And so what I'm going to do is I'm going to flop them between different things, depending on what phase things are in. So again, you group them, all as a unit, and you got to be a little careful with this. Think about, what does that mean? If you're a bash shell, you wouldn't really kind of throw these things into a unit, because God knows what us humans do. Do we compile a bunch of things, run a bunch of find commands, and we don't touch it for another 20 hours? Well, I'm not going to dedicate anything to that. Am I going to do it to my web server that runs on this machine? Well, how does a web server run? Does it run as threads? Most of the time, no. Most of the time it runs as single processes. So I could put all of those into there, and I could say that these are dedicated to these CPUs. But again, because I'm breaking things up and I'm dedicating things, I'm probably going to get that internal fragmentation, where I could have a whole block not being used and something else starving out because they're getting killed. But we have to think about what things would we do here. Now, this one is saying related threads. Now, you got to be careful with threads too, because I think a lot of people think threads are somewhat similar to microservices, and there's one major difference between them. One is that microservices don't run necessarily in a given process. And secondly, microservices are built to be destroyed at any time, and meaning they would run as an atomic function. Where threads, even though they're a function, might have all these interdependencies, related things. They might be blocking. They might be doing all these things. So I don't know, how far I would take, different levels of just kind of saying that related threads are scheduled as a unit. It's just kind of that logic of saying, okay, if I do want 500 of these things all run at the same time, how can I use this, and how can I kind of feather it through the CPUs in a way that makes sense? Now, keep in mind, I went back one side here. What if I have affinity, A has affinity to CPU 0? I'm not going to do this, because that's kind of a waste, right? So, different ways to kind of think about, how we do that. But the idea is that you can have all of them running at the same time on all those groups in that CPU. So you can push them all through, which means your code has to be very designed to do that, right? Microsoft Word and PowerPoint and the 5 PowerPoints really don't make sense to do that, because I don't need to crank things through. I don't need things to run real time. But if I was doing the fastest sorting algorithm in the world, oh yeah, I'm going to try to figure out how to utilize things as fast as I can. So it's an interesting concept, but it's very fit into the exact algorithm that would actually work. So given different CPUs, 0, 1, 2, 3, 4, 5, so you got 6 CPUs against kind of these different time slots, I'm going to start cranking this stuff through as fast as I can, again, based on groups of things. So all the A's, the B's, and the C's together, the D's as much as you can, and then all the E's. Notice this one over here. So what you're trying to do with this is you're trying to maximize everything at the same time, but it's almost like when you see, the Russian army marching. They're all marching at the same time. They're all doing the same things, and that's kind of that whole point of all gang members start and end at their time slices together. They all have to be marching together. It all has to be the same thing, and that becomes pretty difficult in anything that we do in computing, especially anything specific to, anything other than something that's simple and repetitive and is based in time. And that's kind of why we talk about CPU schedulers really can only base things on time, because we don't want to calculate how long a job's going to take. We don't want to go do all that math and then do some weird scheduling thing. We're just going to say, look, you can check out 10 items, you can have it for 200 quantum, and then you go do something else. You wait and you get back in line, and maybe it's you again. But again, with this kind of scheduling and thinking about it, you're basically saying that everybody is adding 1 + 1, and everybody has to be done at the same time, and then it's not uniform. So when we think about CPUs, we can think about CPUs as physical CPUs that I know we've all, well, I don't know if we all have, but I've broken down many machines and ripped them apart and tried to see what it looks like as far as you can. But just knowing that if you ripped a computer apart, a laptop or a desktop or whatever, the CPUs, you pull it out, you get to see the, all the pins on the back side and kind of how it fits in there, and just knowing that that's all the kind of the I/O, the ways that it's given instructions and the way people take instructions from it, and how it goes to memory. But that's the lowest level physical thing. We can then start to get to logical ways of thinking about this in the easiest ways to think about networks, like TCP networks, how the internet is designed, and saying, okay, well, maybe a CPU isn't the unit. Maybe it's an actual computer that might have an OS that would support me asking it to go do work on those CPUs in a general fashion. So I don't know that I'm necessarily on Windows or Linux or Mac or whatever. I'm just saying, run this thing, and I don't care how you do it, just give me the answer. And so we can do a lot of cool things with that. We can do a lot of file I/O stuff, so file systems into NASs and SANs. We can do a lot of data transfer. We can do a lot of interesting logical things when you get into data science and you get into some of the bigger things that we're trying to solve out there with distributed systems, even parallel programming in distributed systems. All of this comes into play. And again, the biggest reason why this is important now, why it's kind of taken off is, just the fact that we have networks that are that much faster. And I'm not talking necessarily, your connection, at home to the internet, which is most of the time pretty amazingly fast these days. I'm talking more about kind of what we've built in systems in standard enterprises where, a 400 gig port, is kind of the main state today. So what am I going to do with 400 gigs? Well, you're going to turn that computer from 24 core processor to 24 of 1,000 processors that all work together across now a network switch layer 2 or 3 that actually connects all those things together. And so this is kind of thinking about how we do packet switching, which is how basically everything rides on TCP/IP networks. And this idea is that, given this 4-port switch, I've got this packet here, and I don't like this representation. I don't think it really shows you much here because it's not showing you the interconnection or whatever. But the idea would be, I've got this packet, and if I'm doing a store and forward, what it's going to do is it's going to basically hit a peer, and that peer is going to take that, copy it, and then send it on as its own. So that's the store and forward. And so the idea would be is as these packets hit, switches are routers. So switches are layer 2, routers are layer 3. Yes, there's layer 3 switches, and there's all kinds of other things that people marketize, but let's just make it simple. As I'm going through a switch, that's kind of peer-to-peer, but as I want this thing to be forwarded on to something else, I'm going to think about that in the layer 3, the routing kind of plane. And that's how things work. So if I wanted to make a request of Google, if I went out right now to google.com and I wanted to go look up apple trees, I'm going to go to google.com, and really when I type in apple trees in the search bar, that word is going to be sent from my machine through some Wi-Fi thing to some endpoint that's my default route. That's going to be a router. So I might flow through the layer 2 stuff, but that's not store and forward. That's just sending it. But when it hits that router, my default route, then what's going to happen is that router is going to grab it, and it's going to strip off the request. It's going to remember that I asked it and how I asked it, which IP address I am and which port. It's going to make that request on my behalf, which might go to another router and another router and another router. Hopefully not too many routers, because then it just takes forever to get it back. But that goes to Google. Google makes a response and then answers back to everybody. And, finally my end router kind of spits it back to me. So that's the whole kind of store and forward mentality. This is achieved by thinking about how do we, in different OSs, and kind of looking at these different nodes, right? So if we've got a physical network interface, these are devices that are, I don't want to say this, they're forms of doing I/O in a computer, but there's a major difference between networks and disk storage. Disk storage is pretty guaranteed. If it doesn't work, you have massive problems, and your machine's probably going to have to be rebuilt, and it's pretty well gone. Networks, they could flake out at any time, all the time, and so now we got to worry about retransmission. And sometimes I would sit there on a blocking call, which I don't do with disk I/O. I mean, there's no point in doing blocking I/O. I just say I want this file, I get it, or I don't get it. But I don't sit here and say, well, tell me when there's something for me. So all this kind of, and when I said polling, synchronization's a bad one, polling's another one. Polling is a bad one too, because you can't just sit there and ask in a while loop, is there anything for me? Is there anything for me? So we had to put in this special thing called select and poll asynchronous I/O to let the kernel tell us if there's anything there for us. Interesting, but still kind of weird and hokey and odd. So being that we've got these network interfaces and we can transfer data through them, we can kind of look at how data gets transferred around to some of these things, but we have to keep in mind that, as a user sends data from, let's say, that 1 to as it goes to 2, I'm making a system call here. Now, I might use something fancy like a send and receive, or this would be a send here, which is a TCP socket call. That's going to eventually call write. Write is going to go to the OS, and it's going to say, use the device driver for the network card. and I'm going to give it everything I need in this whole packetized format, and then that's going to know to route, and the switch really is, in this example, let's call it layer 2, so it just knows where the other side is, and so it determines that and kind of pulls that through, and this was a blocked call, something that was sitting there doing that bad thing. To rip apart this network interface a little more, it used to be that you could only have so many IP addresses per network card and so many different ways to kind of transfer things around. And then probably about, I don't know what it's been, 10 or so years ago now, maybe longer, they actually modified the ability for us to change the code on what's called the APIC. And the APIC is the controller on the network card. So this is given us software-defined networking, which is a whole, just blowing through the market right now, and kind of has, made OpenStack kind of what it was that I've talked about in previous lectures. So just to pinpoint that, the value and what we can do in that space really comes from the fact that, very specifically, we've gone all the way down to here, and we've just opened up something that allows us to kind of control it through different ways and through different programs through user space, which is different than the kernel doing it. We also have something called file system in user space, Fuse, which is the same kind of thing. The only difference is you don't use a network card. You actually use either a network card or a logic that maps what open, close, read, and write would be to a protocol. So it does write on a network card per se, but it's more the protocol of how that works. Again, we do not like blocking calls, but some of the reasons why we have things in the first place is its only job is to be a blocking call. A web server, good example. File servers, they're only sitting there in the world saying I'm here when you want to ask the question. So unfortunately, we have to have these. Now, if we think about this, there's kind of two ways to think about it. Blocking could be any time anybody wants to talk. So again, think of the little kid in the car. Parents are talking in the front and the kid barks in. Well, he shouldn't be able to bark into that conversation, so he's got to wait. And how long does he wait? Or what if, and this isn't how it works in TCP/IP, but just to think of the problem. What if I asked a question of Bob, and as Bob is trying to answer, I'm asking a question of Jane? Now, those two things in TCP work on different ports, so those would be two independent conversations that could flow because they're on two different processes, but just think of that logic. There's a problem there, right? So a lot of what we think about in this blocking concept, and this will be part of what you guys are going to do in Lab 3, which is to do inter-process communication, is how do you make sure that you're not getting the answer before you're done asking the question? And so we'll see that kind of as we kind of get down here. So this could happen. I don't like this diagram, so I'm kind of trying to explain it in different ways. But take the concept that, so I gave the scenario of, one person asking a question when somebody else is. But what if, you can't have two or more people asking you a question at a time? But it's also in this interaction. And if we think about like a telephone call is a good example of a protocol. So the way a telephone call works, we all know it. You ring, the other party answers and says hello usually, and then you say hi, and then you go through, if it's not caller ID and you don't know who it is, then you got to do the old handshake of, who am I talking to, and about, oh, hey, how's it going, and blah, 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 and then you got your chit-chat, your small talk. You get to the meat of the conversation, and then you wind it down, and somebody says goodbye, the other person says goodbye, and you hang up. Well, that's a protocol. Just like there's a protocol like in the Army for how to make your bed and tie your shoes and eat food and, everything. I mean, it's just a defined thing, right? Well, it isn't that computing and messages and how data flows around does that same thing. So you could run into problems where you don't want to be in a non-block, or you want to be in a non-blocking state. You don't want to have to wait for anything, but protocols dictate that you do. So how do we get to a point where we don't have to worry about that? And that's actually this whole thing of asynchronous I/O, which in C code is a selector poll call. We can do it with java.nio in Java. We can do it with different forms of servers. But what we're saying is look, I'm just going to sit here and I'm going to kind of wait with a timeout, but I'm going to ask the kernel to tell me when I can read or write very specific things I care about. So I might be able to say, Bob, let me know when you have an answer, and Jane, let me know when you have an answer, and I'm going to go wait for 10 seconds. And all of a sudden something happens. Now I have 3 questions I need to ask. Was it Bob and or Jane, or was it my timeout? Was it my 10 seconds? Because it could be Bob and Jane. It can't be the timeout because of that, so that's separate. But it could be not Bob and Jane, so on and so forth, back and forth, right? So that's kind of how this whole synchronization thing works. But what we've done is we've gone back to the kernel and said, look, tell me when something happens. And by doing that, I've broken the deadlock because I've gotten rid of one of the 4 things. All these good things kind of come from it. So just a different way to think about it. Again, I'm not going to say blocking is bad. I just really need everybody to understand that when we talk about blocking needs to be managed. It's usually managed through something like synchronization. The worst thing we would do is busy waiting. I showed you that in class, and I think I actually wrecked a OS doing it with 5 lines of code. So think about what really makes sense and really what we need to do. Something I don't know we've talked about much is this idea of copy on write. I think we talked about it in file systems and maybe in memory management. But we will kind of see it again a little bit when we start getting into some of the more advanced stuff down the road, where, and I think it's even a little more in this lecture here, that some, all forms of any form of network storage, whether it's, I'm trying to think of the brand names that are out there anymore, but, Pure or anybody that would do something where they would be some massive storage device, they're not going to have the same copy of the same file for 100 people. They're going to have one file with 100 copies to it, and then when I modify it, then I copy it on write. So that's just a way of saying let's be smart about how we do that. And it could be that maybe we're not dealing with that from a files perspective, but maybe we're dealing with it with a memory segments perspective, or in any other form of something that would do I/O, where there's again that difference between reading and writing. I think my gut tells me that when people started doing socket code, they really didn't like the whole setting up this whole algorithm where you got to, you take all the socket code, and if you want to learn all about this, take my INET4001. You'll know everything you could ever want to know. You're going to build your own web server. It's a cool class. But we talk about remote procedure calls in one of them, and I think the reason why that they became popular is I think people just kind of hated kind of writing all the code, which there's only 7 functions, so it's not that many, but all this logic behind it. So what was created, and Sun Microsystems did this back in the day and created RPC. And what it does is it takes a fully running program, you split it in half, where the main is the client. The main function is the client. It might have other functions to help it. And then you got all the worker functions, and you split them apart. The worker functions become the server. And the server actually goes and registers to the RPC mapper, and it's this whole big thing. Basically says, I'm here, and then the client just kind of compiles it down, and then we use what are called stubs to map the 2 things together through that socket code. So at some point, this client and the server were one piece of code. They got split apart, recompiled, broken up. These stubs are put in there and allowed that network traffic to happen. Now, a couple good things come from this. I can have more than one client on at the same time, and I don't have to worry about different forms of synchronization. I don't have to worry about, I don't care how many are running. It's all taken care of for me. I don't care if this client is Windows and this is Linux, or Linux or whatever. Which is, there's a problem with binary things like numbers, everything but the ASCII table, because we have a problem with little endian. So it's ENDIAN and big endian. What's the most significant bit when we talk about numbers? So there's all this junk that goes into this. That again, that's a whole semester of conversation, but. To make this happen. But RPC was a cool thing that was created, so now boom, I could learn this a little bit, and now I'm a network programmer and I didn't even know it. If you've ever done this in Java, it's called RMI. Why? Because it's remote method invocation, because we don't have procedures in Java. We don't have functions. We have methods. And we don't call methods. We invoke them, or we basically instantiate objects, and they do it. So there's various ways to do it. So many ways to do it. Same kind of logic, same idea. We can take many different machines, and as we've talked about with how we deal with CPUs as different things, we also could do the same thing with memory. And we could say, look, why don't we just have memory that's shared across a whole bunch of different machines? Now, this was never a thing back in 10 years ago, 15 years ago in standard TCP networking, just because we didn't have fast enough networks. Even the fastest I could get maybe 100 meg throughput, and 100 megabits, not bytes, 100 megabits, so divide that by 8, and that's how many bytes you could flow through per second. And when you have 10 or 20 or 50 machines all vying for that at the same time, it doesn't work that well. So the idea would be is we could share memory across different machines, different layers of technology. Just depends on kind of where we want it at the stack. So this is kind of showing, this is basically sharing it at a hardware level, which means this is probably pretty physical. This is getting a little more logical in the kind of super fast things, and then this could be kind of just our standard shared memory distributed system stuff. So another way to think about it too is a CPU can pretend that it's got certain chunks of memory where it can either act as all global, meaning CPU 3 could actually go down and use 7. I could have all of this stuff in some logical plane of its own, where everything is completely in a different space. This gets into some of the value that we're starting to see in. They kind of throw in a software defined. It's really more distributed systems. But this whole kind of idea that, wouldn't it be great to just use the resource we need at the time and then just pay for it when we want to? And this is that whole elastic stuff that we talk about with Amazon, and how we push things around. Now, the reality is that we don't, I don't grab 2.87 CPUs with 487 megs of memory and I use it and then I go away, because there's just too much too much junk that goes around. I split jobs up and I make atomic jobs through microservices, and I make things flow around. So this is a little bit of an odd way to kind of think about it, because it's not really showing you the logical side of things and really how that works. And so this would just be an idea of how things would move around, right? So 10 is going to move from CPU 1 to 0. And keep on moving. Same kind of thing. This is almost analogous to what we talked about with page faults, where everybody thinks they might have access to something that is local that isn't. I might think I have A, that I'm using it for something, but I really don't. In graphing theory, kind of flows everywhere, right? And I always attribute this to maps, Google Maps, physical driving your car kind of maps, because it's it's a game, right? I'm going from point A to point B, and I want to find out the fastest way to get there. This is just a different way to use graphing to figure out how to allocate things as fast as possible, knowing that if you know the index and vertices and you knew the size between them and all that stuff, you could figure out how to lay that out. Now, again, more of an idea that you would have to know all this stuff ahead of time to then go do it. This is where I was talking about adaptive earlier. It'd be great if we could create things that are adaptive to kind of move us through here, but just another model, another idea. So here's the noisy sender-initiated distributed heuristic algorithm. So it's kind of this idea that this is a little more in that asynchronous mode, where you're going to kind of go out and you're going to say, look, I'm going to ask a question knowing that I'm going to get that answer but only because I'm asking that question. So obviously something has to be blocking, something has to be in there to help me manage it, be synchronous and all that stuff. So still at the end of the day, it's, it falls into that. I wouldn't get too locked up into this. It's really asynchronous. Now, the rest of these slides I threw in here, and I think it's kind of an interesting thing that we don't talk about too much anymore, but really understanding what some of these things are and how do we determine what is a valuable CPU? I mean, just because a magazine says it is, or it's 2.7 versus 2.8 gigahertz, is that 2.8 that much better? And it's interesting when you kind of break things down. If you think about a cycle per second, and I believe this is right, is at the speed of light, one cycle would go, I think it's one way to the moon. So that's how fast. So light takes a second to get to the moon. So when we think about, I'm going to do 2.9 gigahertz, that's quite a bit. And we can bring this all the way back down to just regular sound and other things. So really what we're talking about is how much can we do per second? How many jobs can we do? Then we could measure these things on floating point operations per second, and that was just another thing of kind of where we're at. And so this is a year and a half old data, but not much of that changes. Bits we know about, we see that all the time. There is a difference between network being bits per second, not bytes per second. So be a little careful there. And I pulled out, so this is from, and this used to happen all the time, and it was a little hard. It was actually kind of hard to find some of this stuff right now, but this whole idea of, what is the best thing for the best amount of money, and if you're getting into, which we'll talk about in a second, GPU kind of stuff and graphics and all that, everything kind of makes a difference, and there are certain levels and certain things that make sense. In general computing, is it better to put 12 junky things together than 6 really awesome things? And but then you start to look at, okay, well, what can I connect to this, and what's the maximum this and that from an architecture standpoint. So just an example over time. The difference between CPU and GPU. Well, keep in mind that a CPU is there to do a whole bunch of stuff, and it has to hold a whole bunch of information, where a GPU is really there just to make like a calculator in a way, much more than that, but it's more nailed up. I mean, it's more there to just do one thing. So it kind of gives you that idea that I've got, doing some things versus, all of these kind of are managed by a very small thing and just cranking them out. So the reason why this was so great in Bitcoin is that the miners, the things that would actually go try to win, and create that security that is the whole basis of, distributed hashing, was all done through the fact that I could just crank something out, versus if I was here, I'd have to go through some control, some cache, some memory, some back and forth, and at the end of the day, I wouldn't get that much done. I've seen this specifically that as an example for when you do conference calling on a telephone, that means everybody has to be talking to everybody at the same time, which you can't do through technology like TCP/IP. You have to all go through one thing. I know that if you use a CPU, you can get about 20 people on a call, but if you use DSPs, which are kind of like GPUs, it depends on how many channels you have, but for, a price point much less, you could get 128 people on one, or, you could get banks of 128, or, chunk it up however you wanted. This is kind of the whole how GPUs get kind of plugged in through OpenGL, which is just one example through the Linux kernel. So again, I've got my my C library here, my windowing stuff, my 3D gaming, but then I've also got my stuff that kind of comes down more on the GPU side. So how do those things kind of come down and, enter themselves, through DRM down to the GPU is kind of right here. So, and, again, another kind of way to think about it, GPUs kind of being part of what we think about in that whole CPU thing. So, like MMAs and some other things that happen, basically we're using a GPU as its own resource to offload stuff, so we don't have to ask the CPU to do any of that stuff. And when you put it all together, this is kind of a upside down thing that we saw before, but these are the things that we're going to do that are more the real time that can use a GPU, but we do need a way for these things to talk to each other. So as we have kind of this, code that goes through different applications and different modes and layers, it has to go over here and kind of flush through and give the rest of these answers, right? So GPUs in general are, just like DSPs, digital signal processors, and there's a few other things. There's like SCSI controllers and network controllers and all these things that, sometimes you're said, look, the CPU doesn't need to do any of this stuff because it's really, all direct to here. You might have the CPU give it permission through the kernel. You might have to have a flag turned on here and there or get memory allocated, whatever. But a lot of times, if you have application direct access to the GPU, it's up to you how it's used, just like the DSPs are used through different applications. But, different ways of I guess gaining a resource to get things done. So that'll be it for Chapter 8.